start, just please take note and mark your calendar. As announced, we will have the midterm exam face-to-face on campus. I have 2 big rooms reserved and approved it, and then the exact time will be announced. I think it will be the morning from 10 to 12. I have L1 and L2 in the Science Center, so I can spread the group of students out, okay? So the coverage will be, it is on the 20th of March, Saturday morning. The coverage will be announced later as we proceed, and then I will announce the cutoff point. Everything from the beginning to that point will be tested, okay? So you may want to start reviewing. So where we were, this is where we were, okay? So very briefly, I hope that you have this idea to carry with you. This is a good schematic alignment to remember for many atoms. It works. So you see that 2p is higher than 2s, 3p is higher than 3s, but this alignment, sometimes you need to examine closer, okay? Very often 4s is slightly lower than 3p, that's why you first fill in here and then you fill in the transition metal elements that has 3D electrons, okay? Iron, cobalt, nickel, all that in the middle of the 3D row. So those are the magnetic materials, and then the other atomic orbitals. Very roughly, if you have a bigger atom, the 1s is very deep because it sees the whole nucleus. If you look at the hydrogen-like problem, then you will pick up a Z square in front because you see the total ZE charge of the nucleus. Thereby, the 1s will be very deep. A consequence is that will not be involved. 1s electron will not be involved in chemistry. It is the outermost electron that involved in bonding. That's something you learned in the past. Secondly, is that is the source of X-ray. If you use some mechanism to lock this very deep 1s electron out, the highest, the electron in the highest states will come down. Thereby, there's a much big energy difference. The energy comes out as a photon, and you call it the X-ray range. That is why we have characteristic X-ray line, different between one atom to another. And then we also see this difference in 2s, 2p. The reason is simple because it's not Coulombic. It's not strictly Coulombic. And then we also have this difference in the n equals 3 levels, okay? You can get a sense out of it why 2s is less than 2p. If you simply take hydrogen wave function and plot the radial distribution function, that is R squared, the radial path square, okay? You will see for the S state, there is always a little bump closer to the nucleus, which is 0, because the 2s will see the more attractive nucleus that will lower its energy a little bit. So this is the big picture. Then we have remaining question to ask, okay? How to fill in the electrons, okay? We have seen how we can formulate the effective single electron problem in the Hartree or Hartree-Fock way. We have seen that. So we will now look at how to include spin, how to fill spin states in, or more generally, how to fill electrons. What is the rule? Can we put all the electrons in 1s? Okay, why not? So that is the question we want to explore now. So in this part, you can download it from the website. I uploaded it yesterday. You have seen Pauli exclusion principle. I would like in this section to upgrade it a little bit. I would like to upgrade it to a restriction or a requirement about many electron wave functions. How we can write down what is the rule to follow when we write down many electron wave functions. And the rule is closely related to something that we call indistinguishable particles. What it means is that for the 2 electrons living in helium atom, they all live in this 1 angstrom size stuff, okay? And then we cannot distinguish them. We cannot identify electron 1 from electron 2. In a quantum mechanical idea, even within the atomic orbitals, their wave functions, we do not know where exactly one is and where exactly the other one is, and their wave function may overlap. Thereby, we cannot distinguish this wave packet is what electron 1 is where electron 1 is, and the other wave packet is where electron 2 is, okay? Now, if I have an electron here, I have another electron on the moon, then very safely I can still distinguish them. Although, if you talk to a quantum mechanical guy, they will say, the wave function may extend to this side and then they still overlap a bit, okay? But for me, very practical person, if 1 electron here, 1 electron on the moon, I can distinguish them, okay? So the indistinguishability, in my viewpoint, is really related to when we have electrons living together in the same small system. That can be electrons living in an atom, as we are doing, electrons living in a molecule. A molecule, again, is a few angstrom in size. And then the 10 to the 23 electrons living in 1 centimeter cube of a metal. Although it's rather big, but if you look at the number here, there, it's hard to think that their function, the wave function, don't overlap, right? So that is the indistinguishability. In 廣東話 it is 不可分辨的 okay 不可分辨的 It is, to my viewpoint, is more than identical. Identical particles in 廣東話係傳統粒子 okay 傳統粒子 Identical means the electron here is exactly the same as the electron on the moon. Okay, same charge, same mass, same spin half, identical. But here, I would rather stress the point about indistinguishability. They live together in a close vicinity so that we cannot distinguish one from another. Okay, and that will lead to some requirement on the wave function, and that is the discussion here. So what is the outcome? Okay, now if you don't care about all the other discussion that follows, you must take home this thing. So let me state the main result at the beginning. For those who don't like explanation or anything, you may go to the next section. Okay. So the key result of this section is, whatever the way you express the 2 electron wave function of helium atom or many electron wave function of any atom, that wave function must be antisymmetric. The meaning, practical meaning is that it must change a sign. Negative to positive, positive to negative, change a sign, means antisymmetric. With respect to interchanging the coordinates of 2 electrons in the atom. So we have an electron in R1, electron in R2, because in the wave function we have R1, R2, and R1 can take on here, R2 can take on there. Your wave function has a value, okay? Fxy. So you give me an x and y, there's a value. I could replace the x value by the y value by the x value. That is what I meant by interchanging the 2 coordinates. And I require fxy equals minus fyx. That is what this statement means, okay? So take the end result and start digesting as we go on, okay? So this is the requirement taken by nature. Okay, as we will see, why I say this is the requirement, the option taken by nature, because there are 2 choices. But for electron, many electron wave function, this is the choice by nature. So let's see. As I said, it is all has to do with indistinguishability. We will see examples in this section, and the next, it is about the 2 electrons in the helium, 3 electrons in the lithium. But in solid state physics, you have to exercise this rule again for 10 to the 23 electrons in a piece of metal. It's the same requirement. That leads us to look at what indistinguishability does to the quantum wave function. Okay, so that is the question. Why this idea of indistinguishable electrons have something to do with the wave function, the form of the wave function. So here I try to start with the simplest situation where you do have distinguishable particles. By that, I can mimic it as a red ball, a blue ball, so that they are different colors, so I can distinguish them. Okay, so let's consider that we have a 2-particle wave function. I subscript it distinguishable just to make sure that you understand we are not talking about the particular problem that we want to do, the helium 2 electron problem or other atomic problem. It's distinguishable. So I use the first entry. Now there are 2 entries, right? Because I have a 2-particle wave function. The first entry has to do with the red ball coordinates. It has to do with the blue ball coordinates, okay? So this is our red, this is our blue. Now I depict 2 different situations. Situation number 1, the red ball is here at this particular value. So I plug this particular value into here. The blue ball is here, R2. I plug this particular value R2 for RB. So I would plug these 2 locations into my wave function. Then I get a value, a number out, right? It's a function of 2 variables. I plug in 2 locations, I get a number out, okay? Now, if I do what we call the interchanging two particles. That means now I let the blue ball take on R1. It is being here now. The red ball take on R2. Okay? What it means is the following, right? The first entry refers to the red ball. So now the red ball takes on R2, the blue ball takes on R1, and thereby my wave function will have these two values interchanged. You see? This is one value, this gives me another value. All right? Now, they are different or distinguishable particles. The point is, this is a different situation than that. So I shaded this, highlight this point. There are two different situations. Therefore, we really don't expect, and there is no requirement indeed, that this must be related to something to this, because they are two different physical situations. Okay? So here, I hope that you know what we meant by interchanging the variables. Okay? But now imagine, if they are not distinguishable, but indistinguishable particles, just the same thing, the same electron is electron, no red, no blue, one there, and then you say now interchanging, you still have one here, one there, right? Okay, so do you get this point? This is the main physics, the key physics idea. Do you get that? If they are indistinguishable, then this so-called two situations is just one situation. Okay, do you understand? You get this point? If you get this point, then everything follows nicely, okay? So now let's move on. If they are indistinguishable particles, I repeat the argument. The first entry, I call it the A particle, the second entry, the B particle, because I have two, okay? I find some way to call it, but the situation is that on the left, I have the first entry being R1, second entry being R2. In the other way, I already switched interchanged the coordinates of the two particles, but I have one particle here, another particle there, but they are indistinguishable particles. Therefore, they are referring to the same situation. But given a two-variable function, the first one will be like this, that gives me a value. First entry take on R1, second entry take on R2. And now, the other situation, the first entry take on R2, second entry take on R1. There is another value in principle, right? You have a function fxy, two different pairs, okay? But now physics comes in. They are the same situation. Thereby, we would expect some relationship between this number and that number, okay? So the key idea up to here is that they are the same situation. Thereby, there may be some condition relating phi R1, R2 and phi R2, R1, okay? Then we exercise quantum physics. This is the standard shorthand, so let me introduce the shorthand. The situation is actually that one particle takes on that location R1, the other takes on R2, But when they are indistinguishable, we don't know which is which. That is the physical situation. And what we wrote down in many standard textbooks, this will be called PHYS, and this is called PHYS. Okay, so this is what. So what we are saying is that because they are the same situation, there may be some relation between PHYS and PHYS. Okay, so it's rather natural up to here. Then what will be the requirement? Wave function itself does not carry the interpretation in quantum mechanics. According to the Born interpretation of the wave function, it is the wave function square that gives us the probability distribution. Therefore, the physical requirement will be PHYS and PHYS, they are related in the following way. PHYS squared, that value squared must be equal to the other value squared. Okay, so this is the physical requirement. So let me pause here to see whether you follow it up to here. Okay, up to here. Okay, now we have exercised common sense, physical sense, and then we have exercised Born's interpretation of quantum mechanical wave function. Okay, not much new thing. We are just applying what we know. Okay, so this is the requirement. What's remaining is to explore how nature makes use of this requirement. Okay, now let me introduce the name. This requirement is called exchange symmetry. By exchange, I hope now you understand. I'm taking two indistinguishable particles. The location here, I interchange the coordinate, okay? If it has spin, I also interchange the spin. This up go here, the down go there, things like that, okay? But in general, we are exchanging the coordinates of the two indistinguishable particles in the wave function and see what the values come out. The requirement is that the square must be equal to the square, okay? This is the key result. We can generalize it to 3 electron wave functions, 4 electron wave functions, etc. Okay, we have a way to write such thing down later. A key idea up to now is that I hope that you know at this point up to here we have not explicitly referring to a particular way of writing down 2 electron wave function. That is to say, this statement is general in the sense that we have not made use of 1s orbital, 2s orbital. Because when we do that, we are making a further approximation. We are approximating 2 electron wave function by product of single electron wave function. We don't need it to express this requirement in quantum mechanics. I mean this requirement in quantum mechanics. Okay? Now, for those who are puzzling, what does this mean? Okay, so this is very explicit. I have a 2 variable function, so wave function. Okay, so it's a 1D situation, easy, right? So I have a 1D position. This is position A, this is position B. The first entry second entry, function of x1, x2. So x1 can take on A, x2 can take on B. So this is this situation, two locations, you have a number. The other situation is that x1 take on B, x2 take on A, you have another number, okay? Now, if you have this function, you may think about it this way. You can draw it as a three-dimensional picture, right? X1 can take on from 0. This is A, this is B, this is somewhere else. X2 can take on any value. This is A, this is B, etc. So you give me a x1, x2, you can plot the wave function square at the third axis. Okay, so do you follow me? Now put your eye on top view, okay? So now you look down, you will see an XY plan, x1, x2, okay? Now this situation means x1 is A, x2 is B, okay? So you see the cross there? There will be a value of phi square there. You see? This situation refers to the another cross. The first coordinate is B, the second coordinate is A, okay? You use your function calculator, you get another number, square it, there's another value, okay? What quantum mechanics require is the value here must be equal to the value there. Okay, is that clear? Is that okay? Now, let me express it one more time. I can take another point, the circle here, okay? So x1 is long, x2 is short. So x1 is here, x2 is very small, okay? So you have one value here. You use your calculator, two numbers in, one number out, square it. There's a number there at the circle. Now there is a corresponding point where x1 is small, x2 is longer, is this circle. This location, use the calculator, get the phi, square it, you get another number. Quantum mechanics say this number must be equal to that number. Okay, do you follow me? All right. Now, nobody says this number equal that number, right? Because the function of two variables will vary with the two variables. What it all says is a certain kind of symmetry. It says this must equal to that, this must be equal to that for the wave function square, okay? Then you can find all the other pairs of points. Do you find me? Do you follow me? Okay? So this is what this requirement from quantum mechanics means for two particle wave functions, indistinguishable, okay? If they are distinguishable, you don't have this relationship, all right? Now, what is the consequence then? Now that is beyond our quantum mechanics, our level of quantum mechanics. Our level of quantum mechanics says this is, okay, that's it. Okay, we have this requirement very explicitly explained. What does it mean for the wave function itself, not the square? We have two choices, two options. Interchanging the locations, the coordinates, there's no change. If this is the case, this is satisfied. Okay, do you follow me? But there is another situation. If you interchange the coordinate, it's off by a sign. by a minus sign, change a sign. If this is the case, you square this, it is still okay. All right? Okay, so do you follow this logic? The highlighted part is what our quantum mechanics interpretation require for indistinguishable particle wave functions, okay? Now we have two options. Interchanging coordinate of two particles, no change. We call it symmetric wave functions. Actually, technically, in higher level textbook, it is called totally symmetric wave functions. And then the second option is what we need to know for electrons. The wave function is anti-symmetric with respect to interchanging the coordinates of two electrons. This is what anti-symmetric wave function means, okay? So do you know the meaning? Okay. Now, we have two choices, two options, okay? Now, it so happens nature does make use of these two options. For electrons, or a bigger class of particles called fermions, their wave function must obey this requirement. But nature is so clever. There's another class of particles called bosons. The many boson wave function takes on the symmetric option. So nature makes both choices, but use it to distinguish two classes of particles. Our focus is on the electrons in the atom molecules, solids. Therefore, this is important for us. Okay? Now, magically, there is another way to distinguish fermions and bosons. All particles with spin half, or 3/2, okay, half integer, are fermions. All particles with integer spin, 0, 1, they are bosons. This spin and so-called statistics relation can only be proved later in quantum field theory. But we have this relationship, okay? So for those of you who are taking thermal and statistical physics, you will encounter Fermi-Dirac distribution that has to do with this part, okay? For Bose-Einstein bosons, they obey Bose-Einstein particles statistics. It is making use of this part, okay? So for us, we need to know two options, one good for bosons, one good for electrons. Electrons is the only fermions that we will be handling. Maybe in nuclear physics, we have protons, neutrons. They also obey this anti-symmetric requirement. Okay, so that is the conclusion I set out on page 1 of this section. So this is the conclusion after the discussion, okay? When we handle many electron wave functions, including helium ground state, we must construct the wave function such that when we interchange the coordinates of the electrons, it must off by a sign. That is the requirement. This is very general. This requirement applies to electrons in atoms, electrons in molecules, electrons in solids, okay, and protons in nucleus, neutrons in nucleus, okay, all right. But if you have a deuterium, you have one neutron, one proton in the nucleus, they are different particles. You don't need to obey this rule. They are different, right? They are not the same nucleon, all right? So we discussed the whole thing using two particles. That can be generalized to n fermions or n electron. You just take any two of them. Number 2, number 8, the location, the entry, two values, switch it, it must be off by a sign. That is the requirement, okay? And so far, it is a general description. Then the next question to explore is, when we use the single electron atomic state, how can we construct the wave function such that this is obeyed? Okay, so we have 1s, 2s, 2 electrons in there. How can we construct a wave function that this must be satisfied? Because this must be satisfied. Okay, now that is the second topic we want to explore. So next question is, so this is the general requirement, okay? So you carry this into many, many other courses, statistical mechanics, many body problems, solid state physics, you need that. This is general. Now, the question for us becomes, this 32, all right? Now, this is the general requirement. How can we enforce this when we write the 2 electron wave function as some way products of single electron atomic orbitals? We have 2 electrons both in 1s. How to make sure that when you interchange the coordinate, it is antisymmetric? How to do it? It seems rather tricky, right? Okay. Now, for those of you who are going into the advanced quantum mechanics course, or you want to read more immediately, there are different levels. In standard quantum mechanics book, look for the chapter called identical particles. As I said, I rather use indistinguishable. In more advanced quantum mechanics course, you will encounter some new operator called interchanging operator. So Pij operate on a many body wave function, pick out the Ij, interchange it, okay? That is the operation. Or even you will see something rather fancy called the permutation operator. So you have n, 1, 2, 3, something like that. The permutation operator means it tries all the 1, 2, 3, 2, 1, 3, 1, 3, 2, all the permutations arrangement of the variables, okay? That is more advanced level. Nonetheless, I hope I have conveyed the key physical point by simple example of 2 indistinguishable particle wave function, okay? That is sufficient for our purpose. So now the question becomes, how we enforce it when we write the 2 electron wave function in atomic orbital wave functions, okay? So recall, just a while ago, we have discussed and understood, I hope, that how we could have 1s, 2s, 2p atomic state, even in interacting electron systems. Including spin, we would have 1s up, 1s down, 2s up, 2s down, 2px up, 2px down, etc., right? So these are states waiting for electrons to go in. Okay, so now we have a question. Even within this approximation, say Hartree already did the job, how could we construct two electron wave function such that anti-symmetric requirement is observed? That is the question. Okay, let's think about helium ground state. Okay, give me 3 more minutes. I give you something to think about until Thursday. All right, so helium ground state. Everybody can tell me this, I think. The picture is both of them in 1s, one up, one down. Okay, I think every one of you has this picture in mind from high school, from chemistry course. The problem is, write down the wave function for me such that when I interchange the two particles' coordinates, it's off by a sign. Okay? First, I show you something that does not work. It's wrong. Okay? So, how about this? Electron number 1 is in 1s up, number 2 is in 1s down. Now, makes sense, right? Okay? So basically 1 electron in up, 1 electron in down. Okay? I use alpha as the 1, 0 column, beta as the 0, 1 column. That is up, down. You can use a symbol, doesn't matter. Okay? Thereby, my total wave function is a product like this. That makes sense, right? But I superscript it wrong because if I interchange 1 and 2's coordinate, now in this case, 1 becomes 2 and 2 becomes 1. I have to interchange the spin, right? So when I do that, I get that. All right? Now you look at that, it is not off by a minus sign because it's alpha 2 here, the second electron is now down, but it is beta 2 up there. Okay, so simple. Now this is right, but writing it down is tricky. So if you think it is like this, then that is not true. It's wrong. Okay, so what's wrong? Number 1. The point is indistinguishability. We are thinking about a particular one in 1s up, another one is 1s down. But the point is that we cannot distinguish the two electrons. That is to say, we don't know which electron is which. That is the point. Okay? How could we take care of we don't know which electron is which is up, which is down? Okay? If you look at this wrong gas, it does not have any symmetry at all. Okay? I mean the following. You interchange the one. We have shown that this is not off by a sign, minus sign. It is not even equal to that. That is to say, it's not even symmetric. It is not anti-symmetric. It is not symmetric. Meaning, the one we guess is not properly symmetrized. It does not have any symmetry property at all. It's neither symmetric nor anti-symmetric. But I hope that you can observe this, right? Starting with this, I can construct something that is anti-symmetric and symmetric. For example, how about this? You interchange 1, 2, okay? The first term will become 2, 1. The last term will become 1, 2. there's a minus sign, I pull the minus sign out, that is exactly antisymmetric, okay? I can as well construct a symmetric one, okay? So that hints at something. There is a way out now, okay? The first trial is too rough. I have assumed I know which electron is which. 1 is up, 2 is down. I assume too much. Therefore, I know how to write down the right one. I use this and minus this. Okay, so I linear combine this and that. Then I'm sure to get an antisymmetric one. So this is the punchline. Okay, I make sure that I don't know which one is which. So I construct this antisymmetric thing. And that happens to be able to be written as a determinant. Okay, now the first line is the antisymmetric combination. I just decorate the writing as a determinant. This multiply that is the first term, minus this multiply that is the second term, all right? But determinant is nice, right? You interchange two coordinate 1, 2, you are interchanging two columns. It is off by a sign, guaranteed by determinant mathematics. That's nice, okay? Next time, I will start from here and show you the Pauli exclusion principle comes out as a byproduct of antisymmetric requirement of many electron wave function. It's not a principle per se, it is just a byproduct of a higher level antisymmetric requirement. Okay, that's the point I want to convey. So I will stop here. I'm sorry for the overrun, okay, but I think it's the excitement that there is an exciting point up to this here for you to think about. We will pick it up on Thursday again, okay? So done now, I will stay for your questions.